Okay, I think we got this. I'm not sure if it adds on. Hopefully it'll be a separate video. So important thing to do is, like anything, if the ramp is accessible, if you ask someone to make too big a jump, it's not possible. So, which is often true in physics. Then you can get this, but you do have to do that struggle. And it does get easy, but it isn't easy at first. So let's do X versus T first. And let's explore an X versus T graph. Now watch this. First thing I'm going to do, I'm going to go X versus T. So I'm going to put X and I'm going to put the units. And it doesn't have to be meters, but we'll use meters, which is that far. A lot of times 2 steps is a meter really, but a long step. And watch what I do here. I'm going to do something, then I'm going to erase something. You can put the t-axis wherever. I'll put it here. T, and again, I can use whatever units, nanoseconds, but I'll use seconds. So we often put the units. So it's easier. These are little ways to keep track of it. And then I'm going to go like this. I'm going to go like this. Because we don't know what happened before we started our stopwatch. So oftentimes we don't count that time. You could do crazy things, but we usually won't. So that's just, we don't look at that. We just look, start our stopwatch, whatever. So let's look at I'll just make one up. We're going to look at the points. So check this out. We got points. Let's do this. On an X versus time, position versus time, I've got points which tell me X at whatever time or whatever state, X1, T1, X2, T2. I've got average slope. Let me just put average slope, which is delta X over delta T. Oh, that's equal to the average velocity. There it is. And then graphical area. This one's funny. First, I do the math. It's going to be X, or let me do it like this. It's going to be like X times delta T. Remember, anybody good at this always looks at units. They don't skip it. They might do it really fast because they're used to it so much. It's not, that's what an expert, because they always check. This is meters per second. Oh. This is meters times second. That's useless. I don't know, meters times second. What is that? I mean, a meter times a second. So for this graph, that's not anything. You can calculate it. Your math professor could ask you to calculate it and you go, all right, what's it mean? I've got stories. It's okay. Math people don't have to necessarily know their physics. But they can make mistakes. So now let's choose a graph. So let's imagine a motion. Let's say that someone is walking along, and just for kicks, let me call that plus X meters. Let's say this is, well, just make it solid. X equals 0, but you don't start there. You start, I don't know, it doesn't matter. You can start over here. that's x1. Let's say 1, 2, 3, 4, 5. Too many. There. Okay. So that's -2 meters. And then maybe this is x2. And maybe 1, 2, 3. That's x3. 1, 2, 3 is 3 meters. And then they go back. And x4 is 2 meters. Well, what that would look like is, oh, I don't know what time it is. Okay, T1, let's just say that's 0, fine. T2 equals 2, let's say 2 seconds. Let's go ahead and do it. 2 seconds. I'm not worried about sig figs. Oh, T3 is over here. 2 seconds, 9 seconds. And T4 is equal to 12 seconds. Just making it up, whatever. You got lots of exercise, you play with it. Once you get it, you got it. Doesn't matter. Okay, so how do I graph that? Well, I graph that by saying at time T1, 0, I go up to 12. So let me just, that's 6. That's 3. 1, 2, 3, 4, 5, 6. 7, 8, 9, 10, 11, 12. 6 seconds. X, I go up to 3. 1, 2, 3, 1, 2. All right. So I start out here. I go, all right, at time 0, I'm at negative. So there I am. That's 1. At time 2 seconds, I'm at 0. So x is 0. So the motion, imagine it walking up here, but I graph it at 2 seconds. And then at 9 seconds, 2, 3, 4, 5, 6, 7, 8, 9, we're at 3 meters. So the person would actually be moving here. They start here, they go here, they go to 9, then they go back. No, they go to 3, and then they go back to 2. And that happens here. And I can't necessarily draw straight lines. I mean, you could do all kinds of weird stuff. You could go like this, you can go like that, you can go like that. Anything you could connect those points with any curves, straight lines or whatever. We're almost there. I mean, so the actual motion would be start here, you go here, you go here. That's just taking that picture here. I go from here to here, up to here, and back down to here. But this graph is, so you don't move along a roller coaster here. You're moving straight up and down, like that shopping. And so with this, just like you do in the first half of the chapter, you can just do delta x over delta t and d over t. Graphically, the average, the slope from 1 to 2 would be delta x over delta t. And that would give you the velocity on this curve. From 1 to 3, it would be this. From 2 to 3, it would be this. You'd see it there. from 3 to 4, it'd be this. From 1 to 4, it'd be this. But you're just calculating it like you did. But now you can see it on the graph. And the area, even though this is an area, it doesn't mean anything. That's all it is. So you're just graphically representing what you already did. And since I very purposely created this ramp, it's like, oh, I'm familiar with this. It seemed harder at first than it is. Are we okay so far with that?
Yeah.
And then just try, and see my little videos. Now, for time's sake, if I change this and I go, hey, make that V meters per second, keep that T. What changes? Not a lot. What changes is that this becomes your velocity at any time. And the average slope is the change in velocity. I should do my change in some color, like VT, change in V. Oh, that's not average velocity, that's average acceleration. I'm getting used to this. And now the slope does mean something. I'm sorry, the graphic area. I say goes like because it might be a rectangle or a triangle. That's all it's going to be in this class. So it's going to go like V times delta T, which is meters per second times second. That's going to equal my displacement. Before, the slope was average velocity. Now the slope is average acceleration. Before, the graphical area didn't mean anything. Now the graphical area tells me how much displacement I have. So I'm just taking my equations and graphing. And you can do that a little bit with acceleration too. The graphical area is always going to be a triangle or a square or rectangle. Just once you get used to that, you can do whatever. It's going to help you when you do integrals and calculus and stuff too. Because all an integral is like a graphical area. It's the product. But the curves are, so it's useful. But now you know what they mean. And in chapter 6, I connect calculus with this, which will really help for calculus course because it's kind of the missing stuff. And so that's the general. I tried to, here I did a specific, but now I'd have to do specific velocities at specific times and graph it. I can do this. How are we doing on time? You're about ready to go, aren't you, AJ?
Oh yeah.
Go.
Almost forgot.
I could go time and I can go velocity, and then I could put those points on here, and then I could just do this. I just do it, you don't have to be like, just follow the little puzzle. These are your tools. And whatever, however much you do, that'll be how comfortable you are, but you won't be afraid of it for sure. And then you can think about it. AJ, if you have to go, but I can give an example. For example, what you'll do in lab probably. Velocity versus time. If you have a graph that looks like this, I don't know, let's just say this is 1 meter per second. this is 1, 2, 1, 2, 3, 4, 5, 6, 7 seconds. And let's just make this, I don't know, -1 meter per second and 0. One thing to notice is that down here, this is -2 meters per second. -2 meters per second is faster than -1. So things that you play with, there's a lot of thinking in this class. That's why we want to do it before the class starts. It's ridiculously fast. It's really important to get this. That's why it's, but once you get this, you're good because you're going to go over it again. This is going faster and faster, faster in the negative direction. This is going faster and faster in the positive direction. Negative just means the other direction. The slope here would be 0. So that means my slope is flat or 0. There's no change in V over that time. And so slope, which equals average acceleration, is 0, which we call constant velocity. And you're going to see that a lot. It's like, oh, okay, whatever. I don't have to remember all this stuff. I have to remember things like that. I got to know that. Over here, the slope is 0. Acceleration is 0. Acceleration is 0. Here, the slope is equal to change in V over change in T. I go up 1 plus 1 meter per second in 1 second plus 1 meter per second squared. That's the slope. So from there to there, the acceleration was 1 meter per second squared. Graphical area. 1 meter per second times 3 seconds. And that's what? Oh, what is it? I got to write it down. I got to do a bunch till I'm used to it again. Oh, and I'll forget because I got biology class and stuff. That's my displacement. 1 meter per second times 3 seconds equals 3 meters positive is my displacement. My area here is 0, just standing still, velocity 0. And then you go back the other way for 1 second at 1 meter per second. And so there I've got -1 meter per second for 1 second. And that's going to be -1 meter. I'm going to go back 1 meter the other way. Again, area. Half of this, -1 meter per second, 1 second, but half of it, -0.5 meter displacement. There's a lot of information on a graph. That's why we love them, but you got to get used to them. And you guys will do biology graphs and I'll go, I have no idea what I'm looking at, but you spend a little time with them. It totally, the good thing, it disconnects with what we've already defined. You need to put the time in. You need to do these exercises. And this is a huge barrier, but once you're over that hump, then just start helping your classmates because then it'll reinforce it. And you'll have to remind, what was that again? So that was the fastest little intro.
It helped a lot though.
Yeah. Yeah. Cool. Did that make sense?
Yeah, it actually did because I see some of that stuff in my calculus courses and my other, so.
You do. And the cool thing where you guys are and it's fun to see students when that happens. And it was fun for me when you start going, oh, math, physics, chemistry. I didn't get to take biology. It's like I didn't have enough units. God, I like biology, but it's only so much you can do. Yeah, it all starts connecting and you go science, and then like, oh, there's my thing. But I'll tell you, man, our science folks, Dr. Belkowski, whomever, Codeney, et cetera, they're good. They're pretty good at this stuff. They forgot some of it, but they apply a lot of the thinking and the reasoning and stuff. So you can get it. You got to tell, and believe me, I like through all my schools, I can do this. I can do this. If people could do it, I could do it. I just got to put in the time, because I'm totally lost and I'm kind of lost. And then I'm like, I kind of get it, but I kind of don't. And until I keep going, but it's worth it. It's worth it. And that's so work through this book to whatever degree you get will be where you start in the class, not way back here, which is I got to teach the class, so I feel bad because students are dying, and it's got to be taught at this level, and so hence this class.
Awesome. Well, thank